We could look at 3.3 at the end here. All right. 4.2 is generally just Newton's first law. All right. And we're going to look at the correlation between motion of an object and the overall force acting on that object. We're going to determine what's called an external net force. And then third, we're going to analyze problems where there's some sort of equilibrium at play. Take a look at our definition of Newton's first law. Newton's first law. Steph, why don't you read it for us nice and loud? All right, so you've probably heard this before in a general science course or maybe a physical science course if you took that in middle school. What's another name for this law? Anybody know the other name for it? It's a one-word name. It starts with the letter I. You might have heard it if you recall. Louder. Inertia, yeah. Inertia, the law of inertia. Inertia pretty much states this. If I'm moving and there's nothing to stop me, I'm not going to stop. If I'm at rest and there's nothing to push me, I'm not going to start moving. But in life, on the earth, we don't see this all the time because friction is everywhere. So if I were to take my stylus and just slide it across the desk, it should go on forever according to inertia, but it's been acted upon by an outside force. That force is known as friction. Okay? Just like right now, if I'm standing still, I will stay still. If Ed came over and checked me to the wall, I could push this way. Why would my motion begin? Because of an outside force, his push, or whatever it may be. So, in these problems or in these ideas here, we have to consider the fact that an object really doesn't want to move if it's not moving. And it doesn't want to stop if it already is moving. But it will if a force acts on it. Okay, and we call that again inertia. I'll spell it. Okay, the law of inertia. We're going to use the word inertia again today, so you should be familiar with it at this point. Inertia again means an object's tendency to want to stay still or to want to keep moving if it is moving. Now, the next thing we're going to define is called the net external force. You'll hear me say net force. I won't say external. I'll probably just abbreviate and say net force. Find the net force. Find the overall force. Find the net force or find the resultant force. And all this is the sum of the forces acting in a given direction. So, let's look at an example. Can I get two volunteers? Josh? Mike, come on up.
Mike's always volunteer.
Alright, so Josh and Mike, I want you to demo something real simple. Take this chair, alright? And Mike, come on this side. You have more leverage. I want the chair to move that way eventually, but I want you to push against him. But not hard enough that it's going to stop him. So, Mike, you're going to push the chair this way. You're going to push it back this way, but not with enough force to stop him. So it still does move this way. Okay, so right now, pause. If you were to think about this force-wise, Mike is pushing which way? So the word is, for you guys, negative or left, right? Negative or left. Josh is pushing positive. If Mike pushes harder than Josh pushes, it moves to the left. We see that, right? That's all this is really doing here. We're looking at saying which one has a bigger force. At the end of the day, what's the overall force going to be? So if Mike was pushing with 30 newtons and Josh pushed back with 25, that means that the overall force is 5 newtons to the left. Or negative 5. Does that make sense? Okay, that's all it really is. The other class seemed to be confused at first about this. I want to make sure that we're clear as to what's happening. Okay, thanks guys. Really simple, thanks. So, let's look at an example of this that's quite simple. All right, and then we'll look at some of the more elaborate part of the. Take a look at this. Read it nice and loud for us, Jake. Go ahead.
The weight is pulled to the right with a force of 8 newtons, to the left with a force of 115 newtons, upward with a force of 565 newtons, and downward with a force of 136 newtons. Find the net force in each direction.
So imagine this crate is literally suspended in midair somehow. Maybe it's in a magnetic field holding it there. Okay, and it's sitting there, which in that case it would have other forces actually. So let's just say we've got this crate and we know these 4 forces pulling and pushing and everything. How would I draw them? Simply, what would be to the right here? What force? Yeah, 82, right? So let's call that F1. It's pulling to the right, to the left, We'll call that F2. And I'm not putting a negative in front of the 115 because the arrow is indicating that. In my equations, I'll put a negative. Is that clear? When I draw free body diagrams, these things we talked about yesterday, I'm never going to put negatives on signs. The arrow indicates whether it's moving left or right, or pulling left or right, or up or down. 565 upward. And 236 downward. So this is this body that's free in space to move. Which way will it move in the end? Just look at the forces. Which way will it end up moving? Paul? Up and to the left. I absolutely agree with Paul. Does everybody see that? Up is bigger than the down force, so it's going to move up. Left is bigger than the force of the right, so it's going to move left. So in the end, it's going to move left and up. So really, it'll kind of move like this, at an angle, up to the left. Okay, again, it's going to move in that direction generally, because the overall force to the left is bigger than the force of the right, and the force up is bigger than the force down. Now, the question in physics becomes, what's that exact force going to be, and at what angle will it be felt? Remember how we've been looking at objects that are launched at angles, and we break it up into VIY and VIX using sine and cosine? Now we're doing the opposite in this problem. We're going to find an overall x and y, and instead of breaking it up, we're going to put it back together. Okay, and I'll explain how that looks mathematically. So let's look at the two directions here. And the math involved in this example is so simple. Okay, at the beginning at least. We'll get to more difficult in a minute. So in the x direction, what is the net force in the x direction? That's a comma I'm putting there, by the way. F net in the x. What's the net force in the x direction in this case? What would it be? Just tell me how to do it. Yeah, now, yeah, I was going to say use your signs correctly. So, negative F2 plus F1. Remember, F2 is pulling left, so I'll put the negative there now in the equations. F1 is pulling right, so as Ed said, negative 115 plus 82, which, what is the result you said?
Negative 33.
Okay, that's the net force in the x direction. It's simply, God bless you. It's simply looking at the difference in the two forces. That's all you're doing. God bless you. How about in the y direction? What is the net force acting in the y direction going to look like? Somebody else for this one. What is it going to look like in the y? Go ahead.
565.
Give me variables.
F3 minus, plus F4.
F3.
Plus negative, or would you do negative?
That's fine.
Okay, minus 236.
Good.
F4, sorry.
It's all right. Give me the numbers now. Go ahead.
565 minus 236.
So notice Victoria decided to use F3 first. And that's actually, I'm glad, because now we can see that you could either write this as a subtraction, or she was originally saying F3 plus negative F4. It's the same thing, obviously. Okay, you can write it either way. When something is acting up, there's got to be a positive in front of it. When something is acting down, there's got to be a negative. And the same thing came about from the previous line. When something was acting to the left, F2, right, there was a negative in front of it. F1 was acting to the right, there was a positive in front of it. The reason I'm saying this is because what if you have like four forces acting to the right on an object? There's like, imagine like four horses pulling on a carriage, and then friction is acting against the carriage. You're going to have FP 4 times to the right. Those will all be positives. And then FF acting back will be negative. Okay? So you can have multiple forces. So we want to make sure that we analyze all of them. What do we get as a result? 3 what? Close. 329, I think, or something? 329? Not 3.2 and 329. So let's verify that this makes sense. Paul told us about 3 minutes ago that this object's going to move up and left. And that makes sense because left is indicated from the negative 33. Up is indicated from the positive 329. So it's moving a lot more up than it is moving left. So instead of being at like a low angle, it would be at a very high angle. Good, Josh. Okay? So he was going like this because look, this acting up is 329. Acting to the right is only 33. So if I were to look at this as like a triangle, okay, look at this as a triangle here. Right? It's acting to the left with 33, and it's acting up with 329. So it's acting 33 to the left and 329 up. If I wanted to find the overall force, what do you think I'm going to really be looking for in the diagram? Louder. Yeah, the hypotenuse. Very good. If we're looking for, that's an R. Let me erase that and make it better. If we're looking for the overall force, we call that the resultant. Okay, that's an R. So in reality, this is what we're seeing. That's how we have to visualize this in our head. We have to think of it as being pulled to the left with 33, being pulled up with 329. So as a result, it's being pulled left and up. Let's find out what the hypotenuse is to find out the overall force it feels. Okay? This is not drawn to scale at all. You clearly see that? 33 should be like this big. 329 should be like this big. So in reality, if I were drawing this triangle to scale, it would look like this. 33 would be like this, and 329 would be like this. And the hypotenuse would look like this. It would be the right angle right there. Okay, this would be the hypotenuse really. So what you're going to notice is that your answer for the hypotenuse is not going to be much bigger than the height of that triangle. Because they're pretty much close to the same. You see how close they look? Okay, because of this small gap here. So when you solve for R, it's only going to be slightly bigger than 329. Don't let that confuse you and say, oh, there's something wrong with it. The hypotenuse has to be much bigger. It doesn't. You can have a hypotenuse that's very much just like the height, and just a little bit larger. How would I figure out that hypotenuse now that I know the sides of the triangle? Louder. Equals? Yeah, so for me, A is the F net x plus B squared F net y equals C squared. This is how I'm thinking about it. A, right? This is like the triangle again. This is F net x, this is F net y, and this is R. Okay, so this is F net x, F net y, and R. So we take F net x plus F net y, we square them individually, add them together to get R squared. How do I get R in the end of this whole thing? I don't want R squared, I want R.
I have a question. Do you include the negatives?
You're going to square it, so does it matter? But you could if you want to. You don't need them with these. You never need it when you find the result because you're squaring it. Square root, very good. Let's square root the whole thing. So to get R by itself, it's the square root of this whole thing. So it's 33 squared plus 329 squared. When I do this, I get 330.7. Please check to see that you get the same thing. Don't assume I'm right. You know that it's sensible because it's bigger than the other two sides. You know even further that it's more reasonable because it's only slightly larger than the vertical side. And we can see that when we exaggerate in the diagram, that R is only a little bit bigger than F net Y. Just a little bit bigger than 329 is 330.7. So at the end of the day, I could do this. This is why it's really important that we understand this. I could draw the same diagram I started with, this beginning diagram, and instead of drawing all four of those forces, I could draw one force of 330.7 acting up and to the left, and that would be the equivalent of all those other four forces. I could replace this entire diagram with just that red vector with the R there. With only that red arrow. It's the equivalent of all four. That's what you're doing physically. Now the last part we have to do is figure out what's the angle that it's acting at. So again, it could be pulling, the final result could be at a low angle, it could be at a higher angle, up like this. And Josh told us in the beginning, I saw him doing this, it's going to be a steep angle. We can see that because of the shape of the triangle. Look at the shape of the triangle on the left. We're really trying to figure out, let me point to it, this angle right here. Okay, take a look. We're trying to find this angle. And it looks like it's almost 45 in this diagram because it's not drawn to scale. But really it's this angle right here that we're trying to find. That's the theta that we're trying to figure out. Is that clear? That's what we're looking for. The angle above the horizontal. The angle from here to here. Okay, that's theta, right up there, the little black part. So if I were to try to figure out theta, I could use my trigonometry that I learned. Ian, what trig function would I use here if I'm trying to figure it out? Well, cosine is adjacent over hypotenuse. I know the hypotenuse later on, but if I'm looking only at this diagram here. Remember, this is theta, so this becomes what? Opposite or adjacent? Well, sine would be opposite over hypotenuse. You're missing the last one. It's tangent. Okay, let's go back and look at this real quick. We're trying to find theta. We know opposite. We know adjacent. We're trying to find theta this time. We don't know theta. So here's what we write. I'm going to scroll down, but keep this diagram in mind. I'll draw it at the bottom. Okay, again, we're looking for this theta right here. So we take the opposite over the adjacent. So we could say the tangent, because tangent is defined as opposite over adjacent, of theta equals opposite over adjacent. Again, theta is unknown this time. We haven't done this yet. This is new. This is totally new. Okay, the trig idea is the same, but we always knew the angle, remember? I always gave you the angle. You found the side length. Now you know both of these side lengths, and you need the angle instead. There's a function on your calculator that you're going to learn more about this year in math. I'm going to teach it to you now just to use it. I'm not going to go over where it comes from and everything. So take out your graphing calculator, please. So, an easy way to remember this. Whenever you're looking for an angle, right, you need to get rid of that word tangent, really. See how the word tangent is in front of theta? Okay? So it's not the mathematically sound way to say it, but we'll say it this way anyway, because it's easier to remember. You need to take what's called the inverse tangent to get rid of the tangent. Alright? Here's what I'm saying. And if you've seen this before, that's good. So you might be a little bit of jump ahead. But you need to take the inverse tangent of both sides. And inverse looks like this. It means take the tangent -1, like this, of both sides. Now, inverse of a function cancel each other out. They don't realistically cancel, but theoretically they do. So these kind of cancel, leaving behind theta over here. So whenever you're looking for an angle, instead of using the tangent function, you use the tangent inverse function. On your calculator, does anybody know where that is? Catherine? Yeah, so press second tangent. It'll bring up tan -1. Then in the parentheses, put 329 over 33. You need to be in degree mode. So if you want to just hit mode and check to make sure you're in degrees, okay? And then hit enter afterwards, see what you get.
Sorry, like why is it that you're going there if you're multiplying by the reciprocal or canceling?
Alright. The difficult part is to explain this without going into detail. If you want to just memorize for now, when you're looking for theta to get rid of tangent, you use this thing called an inverse operation. And it cancels. These are like the like 1/2 times 2. There's you back to 1, right? like reciprocals.
Yeah, that's-
It's like these are reciprocals or inverses, in other words, we're going to use. So if you take the inverse of this side, go to get rid of this, you get beta. But if you do something to one side, you have to do it together. So you do the inverse of this side also. And it'll give you an angle as a
Like
result.
how come the -1 goes away there even though it's not on the tangent now?
Because you're using it, it's an operation. It's not really an -1. It's an operation. So press on your calculator second tan instead. Again, press second tan, do 329 over 33. What do you get as an angle measurement? Ed, what do you get for this? 84.3
I rounded up.
units of?
Wait, wasn't that the?
It's an angle. What is it? What units?
Degrees.
Degrees, very good. Degrees. Okay, 84.3 degrees. Because there are other measurements of units for angles. So I just want to specify. Remember that term radians and
Yeah.
Fahrenheit? Okay. So 84.3 degrees. This makes a lot of sense. Look at the diagram. That angle theta right here, this angle right here, it's almost 90 degrees. Right? 90 degrees would look like this. Right? So this is around 80, 85 degrees. It makes sense physically because this triangle is so skewed vertically, right? It's like stretched vertically a lot. So that angle theta that you get as a result is going to be something big or something close to 90. So how would I write this? How would I write this answer? I would say the following. Ready? You have a result of 330.7 newtons. That was the resultant force at an angle of 84.3 degrees northwest. Let me explain how I get the northwest part. Okay? Go like this with your arm. Point your arm this way for a second in front of you. So that way, in front of you. Which direction is that? Forget the city. If this is north, this would be west. So, this is west. The minute you start doing this, you're now north of west, aren't you? You're more north of west. You're more north of west. So if you measure this angle here, this is the angle we're measuring right here, this would be west. So it's 84.3 degrees north of west, hence northwest. You see how I'm getting that answer? Okay, you go start by going west, you move up like that, that's the resultant, that's the hypotenuse of the triangle. So it's above west or north of west.
Okay, so what do you, when you would write that answer, what is the question that you would ask? What are we?
The question would say, find the resultant force as one force and find the direction it's aimed at, or the direction it's pointing toward. Here's the resultant force, that hypotenuse we found. Here's the angle that it's angling or pointing toward. Okay? The reason you're doing this is so you can talk about simplifying forces when you have many at once. So a building has millions upon millions of forces acting on it. When engineers analyze buildings, they sum some of those forces together that balance each other out. And they're able to see where they have equilibrium in some spots, or they have net forces in other locations that could cause some issues along the way. So you don't look at every individual force, you sum them together and come up with an overall force acting on the object. That's what we're doing there. Okay, in that example. Now, you can practice this infinitely many times. Just change the numbers. Try new forces, you'll get new answers. So instead of having a force up and down, maybe you have two forces acting up with different values now, and one acting down, or three to the right and only one to the left. But you can try this on your own by practicing more, or just look at your homework. I think one of the homeworks I give you more practice for this. Okay? Use this as a model, please, to help you. Okay, we're going to talk about mass, and I'm going to explain mass to you in a way that has definitely not been explained before. Okay, you've heard of the term mass. When you think of mass, what do you can read the definition yourself for a second. But what do you think of when you hear mass? You hear the word mass. I say the mass of an object is. What am I talking about? What have you heard before? Yeah, like it's weight. You think of weight usually. Okay, now remember mass and weight are different though. Weight is a force due to gravity. Mass, though, is the amount of matter the object has. For example, ready? The mass of this water bottle is the same here as it is on the moon. It's the same exact amount of matter. If I were to be able to instantaneously transport this to the moon, it would have the exact same amount of matter still. It wouldn't change. The mass is identical, but the weight would be different. Because the weight on Earth is more than the weight on the moon, because of gravity. So when you think of mass in the past, you thought of how much stuff you have. That's what mass is, the amount of matter. But this first part of the definition is the confusing part. A measurement of its inertia. Let me give you these examples so you can understand this. If I have a golf ball and a baseball, which has more mass? Thank you. The baseball. Have you ever held the two, right? Baseball is clearly more mass than a golf ball. So if you took a golf ball, put it on the tee, and you drove the golf ball, it might go 300 yards, 400 yards. Put a baseball there. Is it going to go 300 yards? No, it might go like 50 feet, maybe. I don't even know if it goes more. But because the baseball has more inertia, really, we might say it has more mass, so it's harder to move. But mass is a measurement of inertia. Inertia, if you go back and think about Newton's first law, is an object's tendency to want to stay at rest. When the baseball is there and you hit it, it doesn't go as far because it wants to stay at rest more than the golf ball does. It's got more inertia or more mass. So when you think about mass, think about how much inertia it really has. Bigger objects like a mountain, right, versus this table. I can push this table and move it easily while maybe not when the lock is on, but I can lift it and then maybe move it. Okay? Because there's not much mass to the table or there's not much inertia. If you have a mountain, the mountain wants to stay still more than the table does. It wants to stay still more than it does because it's got more inertia or more mass. So that's really how we can think about mass of an object. It has more inertia to it. All right, let's look at an application. It's a really interesting one that most people don't even understand. Ever been in the car before? You hit the brakes, or your mom or dad hits the brakes, and the seatbelt locks. And then the minute it locks, you try to loosen it, it's still locked, and it gets kind of jammed. Okay, let's explain this is how it works physically. Okay, can somebody read as I point? I'll point on the screen, and then I'll discuss it again in a moment. But can somebody just do me a favor? Nice, those are done finally. Just read the paragraph, and I'll point as you read. Go ahead, Victoria.
Seatbelts use the law of inertia to work properly. Once the brakes on a car are applied, the mass under the seatbelt slides forward, which causes the rod to pivot.
So this rod, I'm going to pause you, sorry. This rod pivots like this. This is the original orientation of it. The minute this mass slides forward, it's attached with a pin, which causes the rod to now look like that kind of grayed out area right there. Go ahead.
This causes the ratchet to engage the rod and stop its rotation.
It is called a ratchet. I know you all think of that word differently. It's like a gear with teeth on it that you can lock into. Keep going.
If the ratchet cannot rotate, then the seatbelt is locked and will hold the person in place.
So watch. If you pulled on the seatbelt, it would pull along this pulley, which would cause this to be pulled, and it would cause the ratchet to rotate counterclockwise. But the minute this rod has pivoted due to the mass sliding forward, right? Don't you slide forward when you hit the brakes? On the train, you ever fall forward when you hit the brakes? The mass falls forward. The mass pulls forward. The rod pivots, so it's at an angle. The rod locks into the ratchet. The ratchet can no longer rotate. It stops, and it locks this thing from being able to be moved. Okay, it's really kind of interesting to think about. Now, why does it sometimes get locked afterwards, and you can't disengage it? What happens then?
Oh, because it's still locked.
Yeah, the rod is still locked in it. You need to let go of the seatbelt. Kind of let it go back a little bit, and then the rod will go back to its normal position. If you're pulling on it, there's friction between the ratchet and the rod right here. There's friction there. And if you keep pulling, it's not going to help your case. You got to let go. The rod will then re-pivot back out, and then the ratchet will be free to turn. Okay, but that's how it physically works. So it's using simple laws of inertia. There's no electricity, there's no mechanical nature to it. There's no energy used. You're using inertia to help you in this case. Okay, it's pretty amazing to think about it. A locking mechanism that takes no energy to actually work. Okay, it takes no energy at all. Obviously, you applying the brakes uses energy to stop the car, but you're stopping the car anyhow. There's no additional energy needed. Okay, it just uses some massive object underneath that slides forward, causing this pivot to go boom, and it engages. Okay, it locks in. All right. Last slide for today. Equilibrium. Where have you heard the term? Chemistry. Where else? Biology. In chemistry, you looked at chemical equilibrium. You balanced the equations, right? That was chemical equilibrium. In biology, what was an example of equilibrium? It's a good one I can always think of.
Like in the cells.
Yeah. If the cell is has the same amount of concentration of the fluid outside of it, osmosis will not occur if it's at a state of equilibrium. If the concentration of something is greater outside than inside, the flow will move into the cell, going through those semi-permeable membranes, right? So you have biological equilibrium, chemical equilibrium. Let's look at force equilibrium now. We're going to see many types of equilibrium in physics. This is force equilibrium. Now, if an object is in a state of equilibrium, it means that it's feeling no net force. That would mean this. If I push on this table with the same force that Marcelino pushes back on the table, and it doesn't move. We're both pushing with maybe 20 newtons of force. They're going to push against each other. Is anything going to happen? It's like two arm wrestlers. When they're not moving in the beginning of the battle, they're in equilibrium technically. Okay? Now, if an object is in equilibrium, it means that the net force is going to be zero. Think back to last class. Was it yesterday, right, for you guys?
Yeah.
Yesterday's class. We defined force as something. Force is the cause of what? Fill in the blank. A force was defined in the beginning of yesterday's lesson as the cause of, not friction, friction is a type of force. A force causes something. Acceleration, or a change in velocity. So if there's no net force, then there's no acceleration. Because remember, a force is really the cause of an acceleration. So if you're in equilibrium, ready? I'm pushing. There's no net force. It's zero. Am I moving? No, there's no acceleration here. So I could start by saying the acceleration is zero. If acceleration is zero, I could either be one of two cases. I could be not moving when acceleration is zero, or I could be moving with a what? There it is. Very good. V equals constant. Okay? That's the one that nobody seems to remember that part. When acceleration is zero, you could possibly be at still or at rest. But I could also remember be doing this. Look, I'm moving with a constant velocity. My acceleration is zero. If I'm moving at a constant velocity and my acceleration is zero, it means my net force is zero. So I could have an object moving in space freely like this. Just going like this through space. With no net force acting on it. Just its inertia carrying it through space. And no force acting on it at all. So again, if an object is moving at a constant velocity, it's still in equilibrium. Or it's not moving. It's one of these two. Does that make sense? Is that clear? The definition of acceleration being zero if force is zero. We'll see with Newton's second and third laws, the idea of F equals ma, and we can see how force and acceleration are clearly related to one another. Alright? Any questions on this stuff? Anything you want me to go back to that we went over? Look at the homework room I told you about yesterday. This is 4-2. These are both due on Tuesday. They are both due on Tuesday. They're shorter problems than the 3-3 stuff was. So don't expect it to be like that kind of length, okay?